Namaste student, this is Sanjay Nath. In this session, we learn about rotation and revolution of the earth. This chapter is a part of the unit called Motions of the Earth. Specifically, in part 1, we learn about rotation, ICSE Standard 9. Now we'll watch an introductory visual. What a extraordinary view of Earth in our solar system. Though we can't feel it, Earth zooms through its orbit at an average velocity of 18.5 miles a second. During this circuit, our planet is an average of 93 million miles away from the Sun, a distance that takes light about 8 minutes to traverse. Astronomers define this distance as an astronomical unit, a measure that serves as a handy cosmic yardstick. Earth rotates on its axis every 23.9 hours, approx 24 hours, defining day and night for surface dwellers. This axis of rotation is tilted 23.5 degrees away from the plane of Earth's orbit around the Sun, giving us seasons, day and night. Whichever hemisphere is tilted closer to the Sun experiences summer, while the hemisphere tilted away gets winter. As you can see, the clouds, the part of the atmosphere, veiled our planet Earth. Now we'll begin to understand rotation and revolution of Earth. Now we learn about the motions of the Earth and introduction. In the ancient time, the people used to observe the sun rise in the east, reach to the zenith and set in the west, and the Earth remained stationary. This was the old idea. Before 16th century, the Ptolemaic view was the Earth was at the center and all other celestial bodies was revolving about the Earth. The Earth at the center called geocentric view. Later, in 16th century, Copernicus proved the Earth moves around the Sun and same time rotate on its own axis. As you can see in this picture, Sun is in the center. This is called the heliocentric view, and the Earth revolves about the Sun and same time it is also rotating on its own axis. According to Copernicus, the theory, the Earth have two motions, rotation and revolution. Now we'll watch a video clip to understand this two motion in detail. This is the latest observation and research about the motions of the Earth. Earth revolve about the Sun as well as rotate on its own axis. This jagged motion is called the wobbling of Earth on its own axis due to the gravitational pull of Moon and Sun. Same time, Earth is also moving along with the Sun on an elliptical orbit. Now we learn about the important motion called rotation. Rotation is the spinning of the Earth on its own axis. As you can see in this diagram, this is the axis. Axis is through the Earth that connects North Pole to South Pole. Direction of rotation is always west to east. The time for one rotation is 24 hours or one day called the daily motion. Earth rotation axis is always 23 degrees 30 minutes inclined. The speed of rotation on equator is 1669.9 km per hour. We'll learn this in detail in the next session. Now we'll watch a video clip to understand the Earth's rotation. As you can see, the Earth on its own axis rotating from west to east direction. Earth facing toward the Sun will experience day. Tiltation of axis 23 degree 30 minutes. North Pole and South Pole connected. Earth takes 24 hours to complete one rotation. The part facing toward the Sun will experience day, and the part not facing toward the Sun will experience night. In this manner, Earth rotation gives us day and night. Now we learn the Earth rotation in detail and some facts. Day and night occurrence. As you can see, Earth while rotating on its own axis, the occurrence of day and night happens. More daylight during the summer and less during the winter for the places far from equator. Earth rotate and spin on its own axis. As you can see, the axis connect the North Pole and the South Pole. Location far from equator, the duration of day and night increases. Now it takes 24 hours to complete one rotation on its axis. Due to Earth inclination 23 degree 30 minutes on vertical plane, that towards the pole star, and at the pole 6 month days and nights, it is due to the inclination of 66 degree 30 minutes on elliptical plane. Earth on its own axis, the rotational direction is always west to east direction and is always pointing towards the pole star. The speed of the rotation is constant throughout at any given place, as such we don't feel. There are some more facts about the speed of rotation. The speed of rotation of the Earth on its own axis is constant at any given place and we don't feel it. It's an apparent situation, but there is a different perspective. As you can see that on equator, the distance covered in 1 hour is 1650 km. At the same time, at 66 degree 30 minutes latitude, the distance covered by the Earth is 830 km per hour. At the North Pole, the distance covered by the Earth is 0 km per hour. I believe you understood that due to the curvature of the Earth, in spite of the rotation is constant, the distance covered by the Earth at different latitude it varies. This is one of the very important effect of rotation on Earth at different latitude. Now we'll understand Earth's rotation and its major effects. Due to the rotation of the Earth on its own axis, Earth is flat at the poles and bulge at the equator. As you can see in this diagram, the Earth has been shown from the zenith position, North Pole, and this arrow represents the direction of rotation of Earth from west to east. This blue color or shaded part represents the water bodies, means the ocean, and this ocean is bulged towards certain direction. Due to the rotational direction of west to east, the sun that rises on the east to west side. This also plays a very important role. When the moon and sun come in one row, it started pulling the water from the ocean. It is primarily due to the gravitational pull. It also triggers the tide twice in a day. It is due to the rotation of the Earth on its own axis. It mainly at the interval of 12 hours. There is one more very important occurrences due to the rotation of the Earth is the difference of time. Now we'll watch a video clip to understand why the Earth is flat at the poles and bulging at the equator during tides. As you can see, the Earth and the Moon and the Sun in one line. Together, the gravitational pull of Moon and Sun will attract the oceans on Earth, and this will trigger the tides. Not only the tides, even the Earth, which is rotating on its own axis, that flings off the ocean towards the rotational point. While the Moon shifts its position, the tidal apex also shift. Now we'll learn about Earth rotation and the second major effect. Due to rotation, the winds and the ocean currents tend to deflect. This is a spatial movement of ocean currents and wind system. If you see in the northern hemisphere, the wind and the ocean current, they tend to bend towards right direction, and the southern hemisphere tend to bend towards left. And this force is called the Coriolis force. We'll understand the Coriolis force at first with the help of this diagram. As you can see, this half Earth has been shown over here. This is the side view of the Earth in northern hemisphere. Now this experiment says is a non-rotating frame of the Earth. From the North Pole, if someone launch a bullet, it's supposed to reach towards a target in a straight path. This particular event can be observed from the North Pole, or you can say from the zenithal position. Now from the launch site, if the bullet has been fired, it's supposed to reach towards the target in a straight path. This will only happen when the Earth is on non-rotating frame. As you know that Earth is not stationary, it is in the constant motion, and one of the very motion is rotation. Now if the Earth is on the rotating frame, and every 15-degree longitude it covers in 1 hour. As you can see, Earth on a cross section of the side view, launch side, if the bullet has been fired from here, it's supposed to reach towards the target in a straight line. The different perspective shown here from the North Pole towards the equator from the zenith. The bullet supposed to fire from here reach at the target in a straight line. This dotted yellow line is the intended path, but due to the rotational frame of the Earth and the curvature of the Earth, the object will tend to bend towards right in northern hemisphere, as you can see in both the perspective. And if the same experiment has been conducted from South Pole and bullet has been fired from the South Pole towards the equator, instead of going in the straight path, it will bend towards the left. This is due to the Coriolis force. Now this can be understood very well with the help of this animation. Starting point in northern hemisphere, intended path, the dotted line, and this is the target. Instead of the bullet going straight, it tend to bend towards right. This is the actual path. Now we'll see how the objects behave in the southern hemisphere. Actual point, the target. Due to the rotation of the Earth in southern hemisphere, objects are tend to bend towards left side. This is the actual path, and dotted line is the intended path. This is one of the very important or major effect of rotation on Earth. Mainly it has been seen on wind system and the ocean currents. Thank you for watching the presentation.